Hello everyone and welcome to mechatronics and robotics tutorials by using robot operating system. In this tutorial we will learn how to build a model and simulate a four-wheeled mobile robot in Gazebo. First, we will create a robot geometry from scratch. Then, we will add the dynamical description of the robot and a controller that will enable us to control the robot by using the keyboard keys. Over here you can see the Gazebo simulation of the robot that we will create in this video tutorial. Here you should keep in mind that this is a physics simulation that relatively accurately represents the true dynamics of the robot. We can control the robot motion by pressing the corresponding key. For example, I can stop the robot by pressing K. Then I can move along a straight line by pressing I. Then I can stop the robot, I can reverse the motion easily by pressing another key, and I can rotate the robot around its axis, like this or like this. Behind the scenes, there are several ROS nodes that are running and that enable us to control the robot and observe robot states. The control actions are actually sent as a twist ROS data structure that is converted to mechanical motion by using the so-called Gazebo skid steer drive controller. The model developed in this video tutorial can be improved by including cameras, sensors, lidars, navigation, and SLAM algorithms. We will cover these topics in our future tutorials. The main motivation for creating this video tutorial comes from the fact that you will often need a simulation environment and a digital twin of a robot to verify path planning, navigation, and SLAM algorithms. It is always a good idea to test the algorithm in a simulation environment before you actually implement it in the real-life system. This tutorial teaches you how to build a robot model that can be used for verification of navigation and SLAM algorithms. Also, I noticed that online there are a number of tutorials that explain how to build a robot model in Gazebo and how to simulate it. However, these tutorials are either incomplete or they convey inaccurate information. Consequently, I'm creating this tutorial to once for all clarify all the modeling steps. But before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 400 free video tutorials that you can find on my YouTube channel. Consequently, I kindly ask you to press the like and subscribe buttons. Also, please feel free to leave any comment or a question you might have in the comment section below this video tutorial. Thank you. Here is a brief outline of this video tutorial. First, we will learn how to create a model of the four-wheeled robot by using the Unified Robot Description Format or URDF and Xacro. Xacro is a macro language for URDF files. Then, we will learn how to write a launch file such that URDF models can be interpreted by Gazebo. Then, we will learn how to load the URDF model in Gazebo, and finally we will learn how to simulate the skid steer drive controller for four-wheeled robot. Okay, let's start. In the first step we need to test the installation of Gazebo and we need to install the necessary packages. So let's start. First, start a terminal. And then I'm going to change the size of this terminal such that you can see over here what I'm typing. And I will simply type Gazebo. And if Gazebo is installed properly, you should see this window. If you see this window, then Gazebo is installed on your computer. If not, you need to install Gazebo. I created a separate tutorial that explains how to install ROS. Namely, Gazebo comes with the default installation of ROS. Next, let us verify the Gazebo version by typing this. You can see that my Gazebo version is 11.11. Consequently, everything that I will explain in this video tutorial is valid for this Gazebo version. Next, we need to install the necessary packages. Here are the packages that we need to install. The name of the first package is ROS-Noeri Gazebo ROS package. It is a set of ROS packages that provide the necessary interfaces to simulate a robot in the Gazebo 3D rigid body simulator. It integrates nicely with ROS, and it uses ROS messages, services, and other packages. The next package is ROS-Noeri Gazebo message. This package provides messages and service data structures for interfacing ROS and Gazebo. The next package is ROS-Noeri Gazebo plugins. This is a robot-independent Gazebo plugin for sensors, motors, and dynamic reconfigurable components. Finally, we need to install another Gazebo package, and the name of that package is ROS-Noeri Gazebo ROS Control. This package is very important since it provides controllers and other packages that will enable us to move our robot. Finally, we need to install this package. The name of the package is ROS-Noeri Teleop Twist Keyboard. This package will enable us to control the robot by using the keyboard keys. Let's install these packages. First I'll type this, and in my case you will see that this package is already installed. However, in your case you will see the installation progress. Then run this command to install another package. Then you need to run this command. Then you need to install this package. And finally, you need to install this package. The next step is to create a workspace and the Catkin package for our robot. To do that, we first need to create the main folder of our package. I call this folder robot4, and inside of this folder I'm also creating a source folder. Note over here that you can change this name robot4, however, the name of this subfolder should not be changed. Then, let's go to our new folder for our package, and let's run catkin make. Catkin make will actually initiate the workspace and create the initial package. The next step is to source this file. Inside develop folder, there is a file setup.bash, and we need to source this file. This is a very important step. Next, let's verify the ROS path to make sure that we have properly sourced our package or our workspace. And you can see over here that we actually sourced this folder. This is very important. Next, let's go to the source folder. And let's create the package. Here is the package. To create the package, I'm calling this command, catkin create package. Then, here I specify the name of the package. And over here I specify the dependencies. My package called robot model package will include the following packages: Gazebo messages, Gazebo plugins, Gazebo ROS, and Gazebo ROS control. Note that we have already installed these packages. So let's do that. Let's create the package. Here it is. Step number 3. In step number 3, we will create the source files defining the robot geometry. That is, we will define URDF and Xacro files. To do that, let's move to our package folder, and inside of this folder we will make another folder called URDF. This folder will contain the geometrical description of our robot. Next, let's move to that folder by typing this, and inside of this folder we will create this file robot.xacro. This file will contain the geometrical description of our robot. To make this video tutorial as short as possible, I already created the Xacro file, and here it is. And I will thoroughly explain this file. Also, to make your life a little bit more easier, I will provide a link to this file and to all the files that I will explain in this video tutorial. I will provide a link to my GitHub page, and all the codes will be posted on my GitHub page. Every Xacro and URDF file starts with this line, and you shouldn't change this line. Over here you can see my comments. You use these symbols to start a comment and this set of symbols to end the comment. Then we start the robot section. Over here we start the section, and at the end of the file we end the section like this. Then we specify the name of the robot. In my case, the name is differential drive robot, however you can change this name. Then, you shouldn't change this part. Next, we specify the geometrical dimensions of our robot. However, we use parameters to specify the dimensions such that we can change these parameters as we wish. Here is the top view of my robot showing all the dimensions, except the dimensions in the z-axis direction, however you will see them in the code. My robot is actually a box with the dimension 0.6 in the y direction, 1 in the x direction, and in the z direction it's 0.3. Consequently, I need to specify these parameters. Body link x dimension 1, body link y dimension 0.6, and body link z dimension 0.3. Next, I specify wheel dimensions. Wheel link radius is 0.15, as you can see over here. Then, the length of the cylinder is 0.1, and I need to specify that over here. And I specify the wheel link z location. That is, this is the location of the center of the wheel in the z direction. It's equal to minus 0.1. Next, I specify material density. I have a body and I have wheels. I assume that body and wheels are made of aluminum. And here I specify the density of aluminum. Next, I define the constant. I will need pi constant, and here's the value. I will need this constant to compute moment of inertia, areas, and some other parameters. Next, I need to specify the robot body and the wheel mass. Here's my body mass, and here's the wheel mass. I actually calculate over here my body mass by using these parameters. That is, I simply multiply body density with the body volume of my robot. Then I do the same thing for my wheel. I do it like this. And here's the power of Xacro. You can actually enter formulas like this. You will simply use the $sign, then you will create this section, and inside you will simply enter the formula. Simple as that, and that's the power of Xacro modeling. Over here I compute the moments of inertia of the wheel. This is the moment of inertia with respect to the z-axis, and this is the moment of inertia with respect to x and y axis. Again, I use very well-known formulas given over here for moments of inertia of a cylinder. Next, I define a specific macro. This macro will actually define an environment in appropriate link section later on in the code. I will explain this part later on. Now, over here, I include the file that defines extra gazebo options and motion control drivers. I will explain this file later on in this video tutorial. For the time being, just type this. Over here, I define links and joints of my robot. But wait a second, what are links and what are joints? Let's look into the structure of our robot. Essentially, this robot consists of 5 parts. We have body and we have 4 wheels. In ROS terminology, elements that is the structural elements such as a body, links, or wheels are actually called links. Consequently, I have a body link and I have 4 additional links. I have wheel 1 link, wheel 2 link, wheel 3 link, and wheel 4 link. Then, between every link, I need to have a joint. That is, there is a joint connecting my body link, that is the body, and the wheel 1 link. And the joint is actually shown over here. This is the coordinate frame of wheel 1 joint. Consequently, I have a joint over here, I have a joint over here, and I have a joint over here. Let's define these geometrical elements. First of all, I need to define a dummy link, otherwise Gazebo will complain. And over here, I start my link section, I call the link dummy, and I end the link section. Next, I need to assign a joint to that link. I call the joint dummy joint, type is fixed, and what do I do over here? I specify the parent link will be dummy link, and the child link will be the body link, and that's it. Note again that I need to have this link, otherwise Gazebo will complain. Okay, let's start with the geometry of our robot. Here is the body link of the robot. I start the link section over here and I end the link section over here. Over here is the visual representation of my link. Here I define the geometry. It's a box with the dimensions body link X dimension, body link Y dimension, and body link Z dimension. That is the dimensions of the box in the X, Y, and Z direction. Notice over here that these are the parameters defined at the top of this script. Okay, next, I need to define a coordinate system attached to the center of the mass of my box. XYZ is actually the translation of this coordinate system with respect to XYZ axis and with respect to the coordinate frame or coordinate system attached to the parent joint. And in this case, the parent joint, as you can see over here, is a dummy joint. RPY are roll, pitch, and yaw rotations of the coordinate systems. That is, these parameters represent the orientation. They're all set to 0. Next, I define the collision section. You don't need to know more about the collision section at this point. For the time being, you can just simply copy and paste this part over here. The collision section is very important if you want to simulate the collision of elements. That is, you can detect collisions in that way if this geometrical area is being violated. Next, I need to define the inertial properties of my link. And over here, I define the mass moment of inertia. I use the classical formula. Here they are. This is the moment of inertia with respect to x-axis, this is the moment of inertia with respect to the z-axis, and this is the moment of inertia with respect to the y-axis. And I use the standard formula for the moment of inertia of a box or of a cuboid, as it's officially called by using mathematical terminology. And that's it. This is the body link of the robot. Let's continue with the back right wheel of the robot and its joint. First, we will define the Wheel1 joint. Its frame is located over here. Let's do that. We start the joint environment, and over here we end the joint environment. First, we need to specify the parent link. Let's look at this picture. The parent link is actually the body link, and the child link is Wheel1 link. Note over here that I still didn't define Wheel1 link. However, you can simply write it as a child over here. Next, we need to specify the origin, that is the frame of Wheel1 joint. And as you can see over here, this frame is displaced with respect to the dummy frame. That is, the dummy frame is the parent frame of the body link, and we always need to define the orientation and position of the joint with respect to that initial frame. and we do that recursively. That is, we always specify joint frame with respect to the previous joint frame. This is very important to keep in mind. And here are the dimensions. They are parameterized like this, and these parameters are actually defined at the top of this script. Next, we specify the axis of rotation. Let's look at the picture. We can see over here that the wheel rotates with respect to the y-axis, and consequently over here we have 0, 1, 0. Next, we specify the limit effort and velocity. Then, we specify the dynamics of our joints. We specify the damping and we specify the friction. You can change these parameters and you can tune them. And that was the first joint, that is the Wheel1 joint. Next, we define Wheel1 Link. Here we define the visual description of the link. We specify the origin rotation, that is, we specify the correct rotation. This is very important. Why? Let's look at the picture. If we create a simple cylinder in Gazebo, this cylinder will be extruded with respect to the z-axis. However, we need to rotate the wheel such that it stands in its correct position and location, and we need to perform rotation around the x-axis to bring it in this position. Consequently, over here we specify the roll rotation, that is the rotation around the x-axis, and this rotational angle is actually given in radians. This rotational angle in degrees is actually equal to 90 degrees. Keep in mind here, you need to specify the rotation angle in radians. And over here we specify the geometry of the cylinder, we specify the length of the cylinder, we specify the radius of the cylinder. And that's it. That's the visual representation. Here is collision. Collision is simply obtained by copy and pasting the visual representation. And here comes a very important part. Over here, I'm actually using macros to speed up the coding. That is, to make my code more compact and to speed my coding process. So what's happening over here? Let's go back and let's look into this link, that is, into the body link. If we follow this notation, we will have to define the same section over here. However, we need to do that for all 4 wheels. So is there a quicker way to do that? Yes, there is. We can simply create a macro, and here's the macro, that will automatically add a piece of the code to the appropriate wheel sections, since this piece of code will repeat 4 times. And what's happening over here? We are defining the mass moment of inertia of our wheel. We use the classic formulas for the mass moment of inertia of a cylinder. We specify the mass, we specify the inertia for the x-axis, the inertia for the y-axis, and the inertia for the z-axis, and that's it. So what will happen over here, once this script is being read, the compiler will simply add this part over here, and that's it. Next, we need to create the back left wheel of the robot and the joint. Here's the code. Again, the procedure is equivalent. We define the joint, then we define the link, and that's it. We are actually defining this wheel over here. Again, here is the code such that you can type it. Then, we model the front right wheel of the robot and the joint. Where is the front right wheel? The front right wheel is actually located over here. And here is the code defining the front right wheel. Finally, here is the code defining the front left wheel of the robot and the corresponding joint. Here it is. And we are modeling this wheel. And that's it. We end our file with the end of the robot section. As I mentioned previously, the geometrical description presented in this file is not complete, and consequently we will not be able to simulate the robot only on the basis of this file. That's why over here we're including another file. And the name of that file is robot.gazebo. That file contains additional information that will enable us to simulate the complete robot in Gazebo. And let's create that file. First, let's save this file and let's close it. Then, let's see our file. Here it is. Next, we will create the robot.gazebo file. So we will type gedit robot.gazebo. And here it is. And here I will simply paste the file and I will save it. Let us explain this file. Over here, this code line shouldn't be changed. Again, here are the comments. I start my robot environment and I end my robot environment at the end. First, I need to specify the friction coefficients for the body link. Here they are, 0.2 and 0.2. Then I need to specify the color of my body link. Over here I'm using red color. Then I do the same thing for Wheel1 Link, Wheel2 Link, Wheel3 Link, and Wheel4 Link. As you can see over here, I use the same parameters, the friction coefficients, and all the wheels are yellow. So if you type this code, be careful over here. You need to use this environment Gazebo, and you need to end Gazebo. That is, whenever you want to define any property, you will start the section Gazebo and you will end the section Gazebo. Next, we need to create a section corresponding to the controller for the four-wheeled robot. So what is a controller? The controller is a virtual device that will receive commands from our keyboard and that will transform these commands into robot motions. We will be using the so-called skid steer drive controller. We need to start the plugin and we need to end the plugin over here in the Gazebo environment. We specify the name of the plugin, we specify the file name, and watch out, this is a ROS plugin. And we specify the parameters of our controller. Over here, we specify the control update rate in Hertz. It is 100 Hertz. Over here, this part you should leave empty. Then we specify the robot kinematics. We specify the left front joint, here it is, the right front joint, the left rear joint, and the right rear joint. Notice that these joints are defined in the previous robot.xacro file. Then we need to specify the wheel separation. That is, we are specifying this distance from here to here. And here it is. And we need to specify the wheel diameter. The wheel diameters is actually 2 times the wheel link radius. So make sure that this is correct. Next, we need to specify the maximum torques that our wheels can produce. And over here, since I have a relatively big robot made out of aluminum, not out of plastic, I'm specifying a very large torque to make sure that I can actually move my robot. However, you can modify this parameter depending on the material of your robot and depending on its dynamical properties as well as other properties. Next, we need to define the appropriate topics. We will send the control commands by using the twist ROS data structure. That is, we will be using this standard common velocity topic. This common velocity topic will be used to communicate velocities and angular velocity of our robot. These velocities will be sent actually to the controller, and the controller will implement them. That is, the controller will move the wheels such that the desired velocity is achieved. Next, we want to send some information back, and we are using the odometry topic. Then we need to specify the odometry frame, and we need to specify the robot frame to calculate odometry from. We are specifying dummy. Then we are publishing wheel.tf, that's why we are specifying true here, and we are publishing odometry, and we are specifying true over here. Next, we also want to publish wheel joint state. That's why we have true over here. And this part is required by Gazebo. That is, I need to specify the appropriate covariances. Here they are. Next, let's save this file and let's close our G editor. Okay. The next step is actually to create the launch file and to launch the file in Gazebo. So let's do that. Let's go back to our terminal. Let's go to this folder. And in this folder, let us create a folder called launch. Here's the folder. Then let's go to that folder. And in the launch folder, we will create this file called robot_Xacro.launch. Let's create a launch file. Here's our launch file. We start the launch environment and we close the launch environment. And notice over here that again we have this default line. The first step is to tell to Gazebo the world that we start with. Namely, when we want to simulate a 3D model, we want to actually embed this model in a 3D world. And consequently, we are actually specifying a path to this file, empty_world.launch. This is a Gazebo launch file that inside of itself will launch the default empty world. And over here we specify the parameters. We are using the simulation time. We will be definitely using the graphic user interface. And we specify this parameter, which is not very important, and this parameter that is also not very important. Now, this part is super important. Over here, we actually load our robot.xacro file. This file defines the geometry of the robot. And notice what's happening over here. We are actually trying to locate this command Xacro by looking into the path. Then look what's happening over here. We need to specify a relative path to the robot.xacro file, and we again use these commands. Next, we need to start our Gazebo simulation with the robot state publisher node, and we do that by simply specifying node name and the package. This is the package and the type. And finally over here, we create the 3D model of our system, that is, of our world and of our robot. This is how we do that. We use the URDF's spawner, we use Gazebo ROS, we use this type, we use this command, output is the screen, and here are the arguments. These are pretty much standard parameters. Next, let's save this file, let's close this window, and let's go back to the terminal. Next, let's do the following. We will go to the base folder, and over here we will run again catkin make. Okay, perfect. Next, let us run our world. That is, let us start the Gazebo simulation. To do that, we actually need to invoke a ROS core. To start the ROS core, we will open a new terminal over here and we will type ROS core. This is our ROS master. Anytime you want to run a ROS node, you need to have this program running in background. And finally, we can launch our Gazebo model. So let's do that. Go back to the original terminal and execute this code line, and let's see what will happen. Here it is. Here is our Gazebo simulation. One thing that I like to do is to change the light. So I will click over here and I will add more light over here to my simulation. For example, I will zoom out and I will place the light over here. Then I will do the following. I will click on lights, then here's my light, and I will change it a little bit. I will play with attenuation. Over here there is a constant attenuation, however I will decrease that. And I will do another thing. I will click on pose over here and I will move my light a little bit up such that we can have nice lightning over here. Perfect. However, there is one issue with our simulation. We cannot move the robot. To be able to move the robot, we need to run another node. We need to run this node, teleop with keyboard, and we need to run this Python file. This Python file will enable us to control the robot by using the keyboard keys. So let's do that. I will simply copy this line, then I will go to my terminal. Over here, I will open a new terminal, and in this new terminal, I will simply paste this command. And let's see the outcome. What will happen? Let me expand this so you can clearly see what's happening over here. Let's see what's written over here. We can move the robot by pressing these keys U, I, O, J, K, L, M, and dot. Then we can change the velocities. We can change the linear and angular velocities by pressing W and X for the linear velocity and E and C for the angular velocity. Let's test this. Now, if you would now just click over here, as I did, and if you try to press, for example, the key I that should move the robot, nothing will happen. This is because this terminal, that is, this part over here, should be active when you're doing this. So what I do usually, I actually move my robot over here, that is, I slide the view, then I do this, and I click over here, and now I can control the robot. Let's see what will happen if I press J. If I press J, the robot will rotate counterclockwise around its z-axis. Perfect. To stop the robot motion, press K. Then, let's move the robot along a straight line. To do that, I will press I, and you can see the robot moves. Then again, press K. Then to move in the opposite direction, press comma. Then press K again to stop the robot. Then you can press L to rotate the robot clockwise, and press K. And you can drive the robot like this. Then, if you press U, the robot will describe this motion. Very interesting. It will actually move left or right. So for example, if you press U, it's going to move right. If you press L or O, it's going to move in the opposite direction, side. So U and O can be used to steer the robot left and right, as I'm doing it right now. And I can be used to force the robot to move along the straight line. Similarly, if you press M and dot, you will achieve steering left or right, and if you press comma, the robot will move along the straight line only in the opposite direction with respect to the direction of the I key. And that's it. This is how we drive the robot. Simple as that. Let's press L and O, let the robot rotate like this. Let us now investigate what's happening behind the scenes. To do that, open a new terminal, and in this new terminal type ROS topic list. This will list all active topics, and for us the most important topics is this one and this one. This topic is actually used to transfer commands from our keyboard to our robot. And let's see more about this topic. Let us obtain more information about our command topic. Consequently, I will type this ROS topic info command velocity. And let's see the output. We can see the data type. We are sending geometry messages, twist. That is, we are sending the twist data structure. The twist data structure defines linear and angular velocities that are actually commands for our controller. We can see the publisher. The publisher is teleop twist keyboard. That is, here's our publisher, this node. The subscriber obviously is Gazebo, and Gazebo transfers the information to the controller, and that's it. This is a very important information.